All right, let's get started. Good morning, everybody. Welcome to the physics lecture today. Now, we are going to study about the fluid motion today. And actually, I've uploaded an homework for you probably on last Friday. But some of the questions, actually two of the questions actually is about fluid flow. So they will only be taught in this lecture. And because I have to allow you for sufficient time to do the homework, so I postpone the homework due time to next Wednesday. So the homework due time for this new homework will be on the 6th of April, and that is next Wednesday. Okay, so please be reminded to submit your homework punctually next Wednesday. So let's begin our lecture today. Now, in the previous lecture, we discussed about what is called the steady flow, right, or laminar flow. Okay, in what is called the laminar flow is that if we are looking at a particular point along the flow, then we will find that every physical quantity, including for example, the density and the velocity of the fluid remain a constant, right? So that is called a steady flow or laminar flow. By constant, we refer to a fixed position inside the flow. So we are keep looking at the fixed position, but at different times. Now, but it's important to notice that although the velocity or the density of the fluid at the fixed point doesn't change, it does not mean that the fluid does not accelerate. On the contrary, the fluid does accelerate. Okay, the fluid does accelerate, or because, for example, if the fluid is flowing along a pipe of varying cross-sectional area, then you will find that in area where the cross-sectional is large, then the flow velocity will be smaller. And in the area where the pipe is narrow, then the flow velocity will be higher. Okay, so you can see in this situation, in this analogy of a car moving along the road, you can see that the car does accelerate along the road. Although if you are looking at a fixed position, then you will find that the velocity of the cars that come in and go away, that velocity remains unchanged for a fixed position. Okay, so that is the meaning of steady flow. Steady flow does not mean that the car does not accelerate, but for a fixed position, the velocity is always the same for different car there. Okay, so that is the meaning of steady flow. And for steady flow, we can introduce the concept of streamline. Now, what is called a streamline is that we follow the motion of a particle of liquid. Okay, so imagine now there's a small particle of liquid and we follow its motion. And so its trajectory traces our path along the fluid. And that is called a streamline. A streamline is actually the path traced out by the motion of a particle of fluid along the flow. Now, so because this is a trajectory of the flow, so the velocity of the particle of fluid at a certain instant must be tangential to the streamline. Okay, so we draw a red arrow to represent the velocity at this position, and the arrow is actually tangential to the streamline. Now, for a steady flow, because the velocity is always constant at a specific point along the flow, so that means the streamline will not change with time. So if you are looking at this position, it always have this velocity, and if you are looking at another position, you always have that another velocity. So that those velocity will not change over time. So that is the meaning of the steady flow, and that also implies that the streamline does not change over time. Okay. So you imagine in a steady flow, there are a lot of streamline. and they are all constant, they are all steady along the flow. Now we shall derive an important theorem that's concern the flow of liquid, called the equation of continuity. Now the equation of continuity is nothing. It only reflects that the volume of the liquid is conserved in the flow. Now in the so-called ideal fluid flow, we actually have assumed a important thing is that the density of the liquid doesn't change. We assume that the liquid is incompressible because you need a very large pressure to just compress the liquid by just a little bit. So for most of the situation that we are dealing with, we can assume that the liquid or the gas, even the gas, may be almost incompressible. Okay, so in this situation, because the density doesn't change, so the volume of the liquid will be conserved. Okay, because the volume and the density, they are related by the mass divided by the volume is the density. So if the volume doesn't change and the mass of course doesn't change, the density will also be unchanged. So the density doesn't change implies that the volume of the liquid of a specific mass of the liquid will not remain the same. So that means if I have a liquid flowing into the volume along one side, and there will be another the same volume of liquid will flow out from the other side along the pipe. So that is a conservation of liquid volume. And we are going to derive a formula for that. Now, so how to express the rate of flow of volume of the liquid? Let us consider a surface of area A, which is perpendicular to the velocity of flow. So the V is the velocity of flow, and V is perpendicular to A. Now we consider a small time interval delta t. As you can see from this diagram, we construct a rectangular shaped object with the width equal to V delta t. Now V delta t is actually the velocity, is actually the distance traveled by a fluid molecule in a time delta t. So initially, if you consider any molecule to be inside this cube at the beginning, after a time delta t, they will all pass this volume. They will all pass this surface and flow out of this volume, right? You can think of a molecule which is initially here on this side, and after a time of delta t, it will flow to exactly on the surface A, right? And so any molecule that's inside the volume, they will flow out of the volume through the surface in the time delta t. Okay, so that means the volume of liquid that flows through the surface will be equal to the volume here, which is given by the area A multiplied by the width of V delta t. So this is the volume flow out at the time in the time delta t. If we divide the whole equation by delta t, and we take the limit where delta t tends to 0, that will become the rate of flow of the liquid, the volume rate of flow. That is a volume of liquid passing through the surface per unit time. So dV dt will be equal to what? Will be equal to V8, the velocity of flow multiplied by the area. Okay, so this is simple. If you want to know how much volume of liquid flow through a surface per unit time, you simply multiply the velocity of flow by the area of that surface, and you will get the volume rates. Now, if I consider, for example, the flow of a liquid through a pipe, okay, with varying cross-sectional area. Suppose here at this side, the cross-sectional area of the pipe is A1, and on the other side, the cross-sectional area is A2. So the liquid will be confined here inside the pipe. Okay, suppose on this side, the velocity is V1, and on the other side, the velocity is V2. Because the total volume of liquid is conserved inside the pipe, right? It cannot be more or less because the liquid is incompressible. You cannot compress the liquid. We assume that the liquid is incompressible. so that the volume will not change with time, right? So that means the amount, the volume of liquid flow into the tube on this side must be equal to the volume of liquid flow out of the other side in the same period of time, right? And that means the VDT is constant along the tube. And so that means if I express the VDT with VA, then V1 multiplied by A1 on this side must be equal to V2 multiplied by A2 on the other side. So this quantity VA will be equal. Okay, it will be a conserved quantity along the flow. Okay. In fact, in this example, we have considered a pipe confining the liquid flow. But imagine now, you can get rid of the pipe actually. If you have a flow in 3 dimensions, you can use a bundle of streamline. You can just use a bundle of streamline to construct an imaginary pipe. And all the liquid are actually confined to this pipe, right? Because the surface of the pipe are the streamline, right? So the liquid does not flow out of this pipe, and all the liquid are confined inside. So a bundle of streamline just consists of just enclose a certain volume of liquid inside. And if you consider the one side of the flow and the other side of the flow, you will find that this quantity is going to conserve. So V1A1 on this side is equal to V2A2 on the other side. And that means if this is a constant equal to dV dt, then the velocity of flow will be inversely proportional to the area. So that means if the pipe is narrow, then the liquid will flow faster. And if the pipe is wide, then the liquid will flow slower in order for the total volume of liquid to conserve inside. Now, this is an analogy you have seen before, right? In a previous slide, we have used this analogy, right? If you have some car going through a tunnel, because the tunnel is rather narrow, right? So when you have a car coming from different lanes, they gather around in the junction. At first, they will have a slower velocity. They will have a low velocity because the road is wide. But when it gets to the tunnel, which is very narrow, then the velocity of the car must be increased in order for the flow to conserve its volume inside the tunnel. Otherwise, there will be a congestion of car. There will be a piling of a car at the junction of the tunnel, which is not allowed in our assumption of incompressible fluid or incompressible car density. Okay, so that's why you have a different velocity and you have different cross-sectional area. Okay, remember when you have a steady flows, you always have a smaller velocity at a position with a larger cross-sectional area, and you have a higher velocity in position where you have a smaller cross-sectional area. Okay. Now, so with this proportionality relation, you have this relationship, which I've mentioned. A smaller area indicate a high velocity, and the streamline will be getting closer. Now, because the total number of streamline is conserved inside the pipe, right? So if you have a smaller area, for example, on this side, the velocity is higher. And so the streamline will be more concentrated on this side, right? So the streamline density will get higher. The streamline will be getting closer. So that means what? That means if you see in a steady flow that the streamline are getting close together, that means the velocity there will be large. So the streamline density will reflect what? We reflect the velocity of flow. If the streamline density is high, if the streamline are getting closer, that means that is a region with a higher flow velocity. Okay. So velocity is given by the density of streamline. It's not given by the number of streamline because they always conserve along the flow, but it's given by the amount of streamline per unit area. That is the important idea. Okay, so mathematically is reflected by this relationship. Okay, V inversely proportional to 1/8. And this equation VA equal to constant is called equation of continuity. Okay. Now we are going to derive a very important theorem in fluid flow, which is known as the Boulougner's equation. Now, first we assume an ideal fluid flow, and we assume a bundle of streamline flow through the tube shown here. Now, I divide the tube into 3 regions. The region B it occupies most of the volume of the tube, and there's another region I call A on this side of the tube, and another region I call C on the other side of the tube. So what are the region A and C? Now you imagine that in a certain time delta t, there's a flow of liquid into the tube from the left side. And the amount of the volume of liquid flow into the tube, they occupy the volume A, okay, this region A. And during the same time, there's another volume of liquid that flow out of the tube on the other side. And that is corresponding to the volume in region C. So the volume of region A and the volume of region C are the same, okay? Because the same volume will flow in and flow out in order for the total amount of liquid inside the tube to conserve, okay? Now we use the energy consideration. We consider total energy inside the tube. Now, of course, this energy of the tube, the energy inside the tube consists of 2 parts. The first part is the kinetic energy associated with the motion of the liquid. The other form of energy may be the potential energy, because the tube may be rising or lowering, and the different region of the pipe may have different heights, right? So that they will have the potential energy. Now, but the energy, but this is not a closed system, because there's a pressure on the tube from both sides, right? There's the liquid flowing in, so they exert pressure on this liquid column, and there's also liquid flowing out, so they also exert the pressure on this liquid column. So the total energy, the total kinetic and potential energy inside the tube may not conserve, and we have to apply the work energy theorem in order to calculate how the work done is converted to the mechanical energy. So that is what we are going to do. We consider the work done by the fluid outside the pipe on the fluid. Okay. Now on this side, on the left side of the pipe, the cross-sectional area is A1, and we assume that the pressure, the fluid pressure here is P1. So the pressure force due to the surrounding fluid pressing on the liquid from the left-hand side will be equal to P1A1. This is the pressure force. And the work done will be equal to P1A1 multiplied by the small displacement. The small displacement happens during a small time interval delta t, and the liquid just move into the region A by a distance of delta x1. So I multiply the pressure force by a small distance of delta x1, which denote the work done due to the surrounding fluid on this pipe, pipe of fluid. Now on the other side, we also have another pressure, right? This pressure is P2. And the area, the cross-section area on this side is A2, right? So the pressure force exerted by the fluid outside is P2A2. And since it's moved a certain distance, again, because the water flow out, the work done will be equal to P2A2 delta X2. Now, but why we add a negative sign here is that because the water is flowing out of the pipe, but the pressure is pressing into the pipe, right? So the pressure force and the water flowing direction, they are in opposite direction. So the external pressure does a negative work. So that's why we add a negative sign to the work done by the external fluid. Okay. Now we can easily extract now we can easily see that because the total volume of liquid is conserved, so the amount of liquid flowing into the region in area A, which is A1 delta X1. A1 is the area, and delta X1 is the heights, right? So multiplying the area with the heights will give you the volume V. So this volume V is the volume of liquid flowing into the pipe in a time delta T. And that should be equal to V2A2, which is equal to the volume of liquid flowing out of the pipe. And that is the volume in region C. Okay, now this is nothing but the equation of continuity. Okay, so but we just consider a small displacement delta X. So the A1 delta X1 is equal to A2 delta X2. Okay, so these are the two volume A and C that are equal. Okay, so we extract this factor out, and this becomes P1 minus P2 multiplied by the volume V, okay, inside A or inside C. Now we should equate the work done to the mechanical energy change, and the mechanical energy change is equal to the final energy minus the initial energy. Now, what are the initial position of the fluid? Initially, the fluid. Imagine now the fluid is in region A and B. Okay, so after the fluid, some of the fluid goes into the tube, the sum of the fluid is forced out on the other side. So the whole pipe, the region in the fluid in region A and B will be shifted to the region B and C. Okay, so that is our consideration. Imagine originally we imagined some liquid in region A and B only, but after a while, there are liquids outside flowing in, and so the liquid column will be forced to region B and region C. Okay, we just follow the motion. So the initial energy will consist of the energy of the liquid in position in region B and region A, which is EB plus EA. And finally, because the liquid has moved to region C, right? So the total energy will consist of the energy in region C and in region B. Okay, so the final energy minus the initial energy will be the difference between these two terms. Now you can immediately see that the EB will cancel, and eventually we have the energy in the part C, in region C, minus the energy in region A. Okay, but what are this energy? Now, because the force velocity is VA here, V1 here, in region A, right? So the kinetic energy associated with the flow will be half mv1 squared, where m is the mass of liquid flowing into the volume. So that is half mv1 squared. And on the other side, the flow velocity is v2. So the kinetic energy associated with that will be half mv2 squared, where m is being the same, right? Because same amount of liquid flow in and flow out. And how about the potential energy? We assume that on this side, the height of the liquid above a certain reference position h1, so that the potential energy is mgh1. And on the other side, the height is h2, so the potential energy is mgh2. Now, so EC minus EA become the difference between the mechanical energy in these two regions. Okay, and if we express the m in terms of the density of liquid multiplied by volume, then we can extract a factor rho V out from the equation. Now we now apply the work energy theorem. We equate the work done by the surrounding fluid on the fluid column, which is given by this quantity, be equal to the change in mechanical energy inside of the liquid inside the pipe. Okay, so P1 minus P2 multiplied by V equal to rho V multiplied by this bracket. Essentially, this is a kinetic energy and potential energy in region 2, in region C, minus the mechanical energy in region A. Okay. Now we can see that the factor of V, they cancel out in the equation. And we can move all the quantity with index 1 on one side, and we move all the quantity with index 2 on the other side. So that becomes what? That becomes this equation. P1 rho GH1 plus half rho V1 square is equal to P2 plus rho GH2 plus half rho V2 square. You can see all the quantity with index 1 is on one side, and all the quantity with index 2 is on the other side. Now the quantity with index 1 are just the quantity at the left-hand side of the fluid column. And the quantity with index 2 are just the quantity on the right-hand side of the liquid column. So that means the quantity, this combination of quantity on the left-hand side is equal to this the same combination of quantity on the right-hand side, right? But the two sides are just arbitrarily, right? They are chosen arbitrarily. So that means this quantity, this sum of quantity, P plus rho GH plus half rho V square, this sum of quantity is constant along the streamline. Okay. Now, but this is not a new law of nature. It is just an expression for the conservation of energy for ideal fluid flow. We just consider the work done by surrounding liquid to be just equal to the change in mechanical energy of the liquid column inside. Okay, so this is only the energy conservation principle that we have applied. Now, because we do not consider energy loss due to viscosity or friction, so energy is conserved along the flow. And this equation simply expresses the conservation of energy along the flow. Okay, and formally we call this the Balloonist equation because it is discovered by Balloonists some 300 years ago. Okay. Now let's apply this equation to study a fluid flow. Now, if you have ever taken an airplane, you will find that the passenger airplane will have a small such device at the tip of the airplane. They are called pitot tube, and pitot tube is actually a instrument for measuring the speed of the flight of the airplane. Okay. Now, so you imagine this small tube pointing out, and we just draw a simplified diagram of the tube. Now, this is the point of the tube. This is the part of the tube that's pointing out, right? You imagine this part to be this part, and inside, essentially you have, of course, a real thing will not be so simple, but we just draw a simplified diagram to represent that. We assume that inside the machine, there is a U-shaped tube connecting the two tubes outside, facing outside, and inside the tube we have filled it with mercury, so that the difference in the heights of mercury column between these two sides will measure the pressure difference between the air in these two tubes. Okay. Now these two tubes are facing air. So when the airplane fly, the air will bypass these two tubes. But these two tubes are open differently. For the tube 1, it has an opening on the side that is facing the air. Okay, so when airflow is trying to flow inside, because there are air inside, the air will not allow any further inflow of air. So the air just bypass this tube. Okay, so the flow velocity at this point, which is in connection to the pipe, is exactly 0. So here we have V1 to be equal to 0 at exactly this position. Okay, can you see that? And how about on the other tube? On the other tube, we have a hole, not at the position that is facing the liquid. We have a hole on the side, on one side of the tube. Okay. Now along this tube, this hole is actually in connection with the flow right here, which is another velocity which we call V2. The velocity V2 is actually the true wind speed. It is the flow velocity of air relative to the airplane, and just give the velocity of the airplane itself, because of, the velocity are relative, right? So V2 is essentially the flow rate of air, the flow velocity of air passing through the airplane, which is essentially the velocity of the airplane itself. So if I open a hole here, okay, and the pressure inside and outside of this hole remain the same because the air will not enter, right? So the pressure inside the tube will measure the pressure of air which is flowing at a velocity of V2. So these two velocities are different. They measure two regions of the airflow with a different velocity, and hence resulting in different pressure according to Balloon's equation. Now, Balloon's equation says that if there's a difference in velocity, if the velocity is not the same, then since this combination is going to be a constant, the pressure will also change. If P plus half rho V squared is going to be a constant, neglecting the change in height, which is very small in this case, then if I have a V increase, then P will get smaller. If I have V to decrease to be getting smaller, the P will increase. So the two quantity actually the increase or decrease in opposite way. When one quantity increase, the other quantity will decrease, and vice versa. Okay, so that's an important idea in Bernoulli's principle. Whenever you have a region of slow flow velocity, of small flow velocity, you have a high pressure. Whenever you have a region with a high velocity, you have a small pressure. Okay, and that exactly reflected here, right? At this position 1, we have a zero velocity, and we have a high pressure region P1. At this position, we have a large velocity of flow V2, and so it would have a lower pressure P2. And so the difference in pressure is reflected here by the difference in the mercury column. And we assume that the two sides of the mercury column, they differ by height of h. And that measures the pressure difference between these two sides. The Balloon's principle says that P2 plus half rho V2 square is equal to P1 plus half rho V1 square, but V1 is 0. So we have this equation, and we can solve for V2, which is essentially the velocity of the airplane. So the velocity of the airplane is square root of 2 P1 minus P2, the pressure difference between these two sides, divided by rho square root. But the pressure difference P1 minus P2 is equal to the density of mercury multiplied by G multiplied by H, which is the fluid pressure of mercury. Okay, so after you measure this H, you know the pressure difference, and if you know the pressure difference, then you know the velocity, and that is one way for you to monitor the velocity of an air flight. Now, nowadays, there are multiple devices on the airplane, which are mostly electronic, that can monitor the speed of the airplane. They check each other. They are checking each other so that to reduce the chance for mistake. Okay, so they have multiple devices, and one of these devices is the pi dot tube. Now, we recently have an unfortunate accidents of an airplane crash in Guangxi of China, right? The airplane just crashed vertically. Airplane crash just happen occasionally. And I want to tell you about a incident that happened in 2009, the 1st of June. That happens almost more than 10 years ago. Okay, it happens that at that instant, an Air France flight 447, it depart from I think it depart from Brazil a city in Brazil, and it will expect to arrive in Paris several hours later. But somewhere in the Atlantic Ocean, the flight lose contact. It lost contact, and eventually we find that it just crashed into the sea. Now, what happened with actually what happened with the flight? We believe that there are temporary inconsistency between the airspeed measurement. It is quite likely due to the aircraft pilot tube being obstructed by ice particle, because the airplane is flying high into the sky, and the air temperature is very low there. And if the humidity at those positions is high, there may be ice crystal forming inside the pilot tube, and that blocked the pilot tube from meeting the surrounding air, and that result in a wrong measurement in the speed of the airplane. And the pilot doesn't know. They didn't know. They thought that there was a fault in other instrument, because they do not notice the inconsistency is due to the fault of the pilot tube. So they keep on accelerating the airplane until it becomes too dangerous. It becomes too impossible to revert. And so after reaching a very high velocity, the airplane suddenly lose control and descend, and that result in a crash. And that was a very unfortunate accident. Okay. Now let's talk about how an airplane fly. Now a typical airplane will have a wing with cross-sectional area that takes this shape. Now I do not draw it very well, but it is more curved and on the upper side, and actually is more flat on the lower side. Now, this is not the only factor that contribute to the lift, to the lifting force of the airplane. In fact, the airplane usually has its wing tilted at an angle when it is ascending, and that also contribute to the lift force on the wings of the airplane. Okay, so both the angles of attack and the wing shape, they both contribute to the lift force. Okay. Now, we want to study what would happen when the air flow passes the wing. Now, the experimentally, they found that when it flow past the wing of this shape, and when the wing is tilted, the velocity of flow on the upper side of the wing is not the same as the velocity at the lower side. The two velocities are different. And they found that the velocity on the upper side is higher than the velocity of air on the lower side. There's a difference in velocity here. And in this figure, we can say V1 is larger than V2. Now we look at the Bernoulli's equation. Because the heights of the airplane, of the wing, is so small that we can neglect the difference in air pressure, in potential energy. So we don't consider the term rho GH. We only consider the combination of P plus half rho V squared. On the upper side, we have P1 plus rho V1 squared. On the lower side, we have P2 plus half rho V2 squared. For simplicity, we assume that the rho to be the same. Essentially, this is true as long as the flow speed is much lower than speed of sound. Okay, but the difference in velocity will give rise to a difference in pressure. A larger velocity, a larger V1 here, will imply a smaller pressure on the top side. And a smaller velocity of flow on the lower side, on the lower surface, will imply a larger pressure on the lower surface. So the surface, the pressure on the lower surface, P2, is larger than the pressure on the upper surface, which is P1. Now the surface on the the pressure on the lower surface is pointing upwards, while the surface on the upper surface is pointing downwards. So now it is the lowest surface which has a higher pressure. And that means the net force the sum of the pressure of the two pressure force will produce a net force, which is pointing upwards. And that provides the lift of the airplane. The lift force of the airplane counterbalance the weight of the airplane. And that's why the airplane can fly up to the sky. Okay, so it's due to the pressure difference between the upper and lower surface that provide the lift force. Now we have a so-called wind tunnel experiment. Now before those days where computer simulation of airflow is possible, the scientists or the engineer, they perform a wind tunnel experiment. Essentially, they have a smaller version of the airplane wing to be put inside a long tunnel. Okay, so essentially this is a cross section of a wing, but in a smaller scale. They put it inside a tunnel, and then they blow air from one side of the tunnel, and the air will flow through the wing, and they measure the lift force. And they measure the lift force, for example, for different shape and for different angle of the wing. Okay. Now, to make the flow velocity visualize, to make the people visualize the flow, some experiment may put some smoke. Now, this streamline is due to the smoke. If I put the smoke here, if I release a small amount of smoke here, they will just follow the streamline. Okay. Now, this is a continuous flow. Now here we have a snapshot. You can see along the flow streamline, the flow velocity here at the top of the air of the wing, at the upper side of the wing, is faster. You can see the streamline is getting closer. And actually, this is the case. You can see the streamline there is more closely squeezed together, and so they flow at a high rate. Now you can see the air reach the middle of the wing here on the upper side, but on the lower side, it only reached the front part of the wing. So there's apparently there is a difference in flow velocity. Okay, the velocity on the upper side is higher than the velocity on the lower side, and it's become apparent even if all the air has passed through the wing. Okay, now I have a video for you to see the effect. Now, this is a nice video created by a new scientist. Now you can see the smoke here, right? Now this is the turbulence, the vortex happening, but we won't go into the turbulence features. Essentially, these are steady flow in the middle part. Now let's take snapshot of the fluid motion. Let's proceed step by step to see how the fluid flow, the air flow through the wing. So the air is coming now along the same wavefront, but after meeting the front part of the wing, you can see the air on the upper side is flowing much faster. Now the streamline are compressed here, right? Indicating high velocity flow at the upper side. And even after it passes through the wing, the upper air still flow with higher velocity. Okay, so this is about the case. Okay, is that clear? Now, so we have the pressure difference between the two the upper and lower surface of the wing to be equal to P2 minus P1, right? And the net force is upward. So I have P2 minus P1, and my balloon squeezable is equal to half rho V1 squared minus half rho V2 squared. Now the lift force will be equal to the pressure difference multiplied by the cross-sectional area. No, sorry, not cross-sectional, multiplied by the area of the wing. The area is the upper or the lower area of the wing. They are about the same. So we just multiply the difference in pressure by the area to get the lift force. Okay, and by the balloon's equation, this is equal to half rho A V1 squared minus V2 squared. Now experimentally, people find that the difference between the velocity square on the two sides of the wing, on the upper and lower side of the wing, will be proportional to the square of the velocity, which is has a far distance from the wing. So V1 square minus V2 square is proportional to V square. V square is the velocity, the initial velocity of the incoming air. Okay. Now this is an experimental fact. I cannot explain to you clearly, but people find it to be so over a wide range of velocity. So in that case, we can define a proportional constant, which is known as CL. V1 minus V2 square, we can write as CL V square. And CL is a coefficient called a coefficient of lift. It depends on the cross-sectional shape of the wing and also the angle of attack. Okay. And so we can write the lift force as half rho ACL V square. Now you can see that this equation is actually very similar to the air resistance equation. Now there are two main differences. The first difference is that this CL is not CD. This CL is a coefficient of lift. It is different from the coefficient of drag. Okay. The other difference is with the A. The A now not is referring to the cross-sectional area anymore. It refers to the surface area of the wing. So the upper surface area of the wing and the lower surface area of the wing, we assume that they are almost the same. Okay, and you should count that area instead of the cross-sectional area. Now, because for airplane, the lift force has always to must balance the weight of the plane, right? Otherwise, the airplane cannot fly. So the lift force must be at least be equal to or larger than the weight of the airplane. Otherwise, it will fall down. Okay. So when the plane is landing or taking off, the velocity of the airplane may be smaller, and the lift force, the resulting lift force, may also be smaller. So people have to find ways to increase the lift coefficient in order to provide extra lift for the plane to take off and land. Okay, now this is the problem when the velocity of flow is small. When the velocity of airplane is small, you have to increase the coefficient of lift so that the plane can take off and land safely. Okay, and that can be achieved by two methods. Now, I don't know if you have traveled before by airplane. If you have done so, then you must have seen, if you are sitting close to the airplane of a flight, you will see that the wing flap is a small area of the wing at the rear part of the wing. Okay, you will see during the takeoff and landing of the plane, the wing flap will lower, so that the shape of the airplane wing will be changed by lowering the wing flap, and that will essentially increase the air drag. The drag force will be larger, so the plane will decrease in velocity, and it also increases the lift coefficient, the coefficient of lift, to provide more lift force for holding the plane up. Okay. So lowering the wing flap will provide you with a higher coefficient of lift. And also during the takeoff of an airplane, the wings is usually inclined at a small angle. Now this angle is usually less than 10 degrees. But using a small angle of attack, this is called the angle of attack, will increase, the high angle of attack will increase the lift coefficient also. Okay. So that's how you adjust the coefficient of lift. Now you are going to estimate the takeoff speed of Airbus 340 and the minimum length of the runway. You will be able to understand why the length of the runway have to be as long as 1 or 2 kilometers or so. You can see your homework to see how a large passenger plane take off. Okay. Now this is an app called Wind Tunnel. You can actually download it in Android or iPhone. I like playing it around with this all the time. Now, it allows you to design your own cross-sectional area of the wing. Now, this is what I draw. You can actually use your finger to draw the shape of a wing, the cross-sectional shape of a wing into a wind tunnel. And you can see the air passing through the wing. And you can see the smoke here, and you can see the drag coefficient and the lift force acting on the wing. You can design different wings to see the effect. And if you press the speed, if you press this button, you will see the difference in the speed. Now you can see the red part and the pink part, and the violet part. They have different speed, and in fact the flow velocity is higher on the upper side of the wing. Okay, you can easily see that this red part corresponding to a high velocity, and you can also see the pressure by pressing the button pressure here. You see that the lower part of the wing actually have a high pressure, where the upper part of the wing actually have a lower pressure. Now, so you just download this and enjoy it. If you like it, you can buy it with several tens of dollars to enjoy the advanced function, and that allows you to investigate different wing shape very vividly, and that's quite interesting. Now let's stop here for a break. All right, we may continue now. Before the break, we have mentioned that in order to increase the lift coefficient when the plane is landing or taking off, the angle of tilt, the angle of attack of the wing will be increased, right? So people have to find some ways to tilt the airplane in order to increase its angle of attack. Okay, so how do we change the angle of attack? How do we tilt an airplane? How do we tilt up or even tilt it down? Now, the secret of tilting the airplane actually lies on the principle of torque or principle of moment you have learned in the previous course, in the previous chapter. Like this is a simplified diagram of a passenger plane. Now it happens that the center of mass does not coincide with the center of lift of an airplane. Now the center of mass is somewhere here. The center of mass of the whole plane, including the passenger, is somewhere here, which is slightly in front of the wings of the airplane. So the wings of the airplane is there, and the center of mass is slightly in front of it. So there's a small distance between the center of the airplane and also and the center of mass position. Now, but the wing produces a lift force, right? So the force will be acting on the position of the wing, right? So effectively, we can denote a certain point, which is called the center of lift. The lift force will be concentrated at this point. So you can imagine that the pressure force acting on the wing will be all concentrated at this point called center of lift. So the lift force will be pointing upwards at this position. Now, but there's a small distance between the center of mass and the center of lift. So that small distance will be called dl. Now you can easily see that if one of the force, the lift force go up, and the center of mass, the weights acting on the center of mass goes down, it will turn the airplane in the anti-clockwise direction. So if the plane is left like this, it will be turned in the anti-clockwise direction, which is very dangerous. It will have its nose pointing towards the ground, and it will directly crash onto the ground, right? So how do we fix that? How do we rectify that? Now the answer is by the tail lift. Now that you can see there's a small wing at the end of an airplane, at the rear part of the airplane. There's a small wing called tail wing. Now the tail wing is actually tilted like this, so that it produces a lift that is in the opposite direction to the lift force. So the lift force is going up, but the force acted by the wind pressure on the tail wing is direct downwards. Okay, so because the wing is tilted like that, but not like this, it's like tilted like this, it's pointing downwards. So the tail wing receives a force which is vertically downwards, and we call it a tail lift. We call this force tail lift, T. Now you see there's a chance of balancing. Now because of these two forces will generate a anti-clockwise moment, right? But this force will generate a clockwise moment, and it's a large distance dt from the center of mass position. So there's a way to balance the whole plane. If we take the moment about the center of mass, then the tail lift will produce a clockwise moment that is equal to TDT. That is the torque produced by the tail lift. And the anti-clockwise torque produced by the lift force will be equal to L, the lift force multiplied by this small distance dl. You take the center of mass at the pivot position. We take it the moment about the center of mass. Okay. So this condition actually can be satisfied if I suitably adjust the angle of tilt of the tail wing. Now, but when the plane is taking off, people will adjust the tail wing tilted at a high angle, so that the tail lift will be larger. Now, imagine if this tail lift is larger, then the plane will turn clockwise, and the tail of the plane will be lowering. So in opposite side, the tip of the airplane will be pointing up, so it will be tilted upward. Okay, so and that's how we tilt the plane and adjust the angle of attack, increase the angle of attack so that it can gain more lift during its taking off motion. Okay, so that's how people adjust the angle of tilt or the angle of attack of the wing. Okay. Now, but that could be dangerous in some situation. Now, you recently have heard about the crash of an aircraft in Guangxi of China, right? Now that accident happened because there may be a bug in the software of the airplane. Okay, that airplane maybe have a bug in the software. So when it actually correct the software actually correct the lift force in the tail wing too much. Now because when the airplane is gaining speed, okay, the tail lift will be higher. Okay, so the plane will have its tip tilting upward, and the software tends to correct that. It makes the airplane tilt downwards to balance that increasing lift. Okay, but it seems to be in certain situations it seems to be correcting too much, and it will make the plane out of control. Okay, and eventually it crashed vertically downwards. Okay, so that is the major bug maybe in the design of the airplane, and that needs to be rectified, of course. Now, at the end of the chapter, we let us study an example of water leaking out of a small hole at the bottom of a tank. We suppose we have a container. We have a container of a large cross-sectional area A, and that container is filled with liquid, and we denote H to be the height of the liquid above the bottom. Okay, and at the base of the container, there is a small hole with area A0. Now, A0 is much more than A because it's a small hole. When compared with the cross-sectional area of the container, it is negligible. Now, we will actually relax this condition in some situation. We may study it in the exercise class or also in the lecture, okay? In some situation, A0 can be comparable to A. But now for this situation, let us ignore A0 with respect to A when we compare them. Now, so we imagine now the liquid to be flowing out along a streamline. Initially, the water molecule to be at this position at the top of the surface, and it slowly flow out along a streamline like this. Okay, so we are apply the ballooning principle along such a streamline. Now, on the surface of the liquid, on the surface of the water, the pressure is equal to the atmospheric pressure. So we have P naught. And since the surface of the liquid is a height h above the base, we choose the reference position of the potential energy to be at the base. So the potential energy term will be rho gh. Okay, and since the liquid is descending slowly, the change in the height of the liquid is very slow compared with the ejected speed at the hole. So we can neglect the descent rate of the liquid. The velocity here can be taken essentially as 0. So we neglect the kinetic energy term. The half rho v squared on the surface of the liquid is negligibly small. Now on the hole, at the position of the hole, the pressure is also P naught. It's an atmospheric pressure, because as soon as the liquid come out of the liquid, of the bulk of fluid, it's exposed to air. And when it's exposed to air, the pressure is the atmospheric pressure. So the pressure of the liquid here is P naught again. And the potential energy is 0 because it's a reference level. And we assume that the liquid come out as a velocity v. So kinetic energy times half rho v squared. Okay. Now, so you can see that the term P naught will cancel on both sides. And the velocity will then be equal to square root of 2gh. So that the velocity is exactly given by 2gh square root. Okay. Now you can see that this expression is identical to the expression you learned in high school. When a body falls from rest by a height of h, it acquires a speed that is equal to square root 2gh. And that can be derived from the conservation of energy, right? By the conservation of mechanical energy, potential energy loss equal to kinetic energy gain, and you arrive at the same expression. Now that is not surprising, because the balloon's equation is actually representing the conservation of energy. It's not a new statement in physics, but it's essentially the conservation of energy. So it gives you the same result of the velocity of flow leaking out of the hole be equal to square root 2gh. Now, but the volume of liquid has to conserve, right? That's equal to dV dt. And on the surface of the liquid in the container, the rate of change of the heights is dh dt, and this is the vertical speed of descent of the fluid molecule, right? And if I multiply this speed with a, I got the volume rate of flow. I got dV dt. This is the equation of continuity. Okay, and that must be also equal to the amount of water flowing out, which is the velocity of flowing out multiplied by the area of the hole, A naught. I might put a negative sign here because by definition, the V is positive, but the HDT is negative. So in order to make the sign right, I have to manually add the minus sign here. Okay. Now, but by the balloon's equation, I got the V. The V is square root 2gh. So I can substitute the V into here. And I eliminate the V totally. And I get a simple differential equation of this form. Okay. dH dt equal to a constant multiplied by square root h with a minus sign. Now, this equation can be integrated. If I move the square root h to the left-hand side, and I move all the constant to the right-hand side, I can integrate over the h on the left side and integrate over time on the other side. Initially, I assume that the height of the liquid column is h naught, and that happens at the initial time t equal to 0. At the final time t, the height of the liquid column is h, so that corresponds to the upper limit here. Okay. Integrating 1 over square root h is square root h divided by 1/2, and that becomes, when you vary h over h naught, that's become h square h naught minus square root h. I divide the two equation by 2, and I put a minus sign on the left. Okay, and of course, integrating the dt becomes t. Okay, so this is the relationship between the height h of the liquid column and the time t. So it's expressed the height of the liquid column at different time. Now, we also want to find the time to empty the tank, and that should correspond to the height being is 0, right? So we put 0 in this equation, and we solve for time. The time is given by this. Okay, so that completes our problem. Now we have a small extension on which called voltricity. Now voltricity will involve a very complicated phenomenon, which I will not test you in an exam. But I just want you to know is there. And I just want to show you this interesting phenomenon by using a simple, interesting experiment of an air gun. This is an air cannon, a so-called vortex cannon. Now, what is that? Essentially, this is a bucket. You can take a bucket at home, and you drill a small hole here on one side, and on the other side, you can cover it with some plastic sheet. You fix the plastic sheet on the other side of the bucket, and if you press on the bucket and on the plastic sheet, the force, the change in pressure inside, it will cause the air to flow out of the hole on the other side. And it happens that the flow velocity at the center part of the hole is highest, but the velocity near the rim, near the inner rim of the hole, it will be affected by the hole because there is a drag force here due to the rim of the hole. And the difference in the velocity between the central part and the outer part will cause the air to rotate. Now, this is due to the viscosity. If you have two layers of different velocity, one flowing past the other with a high velocity, then you set the rotation. You set the slow layer into rotation, okay, because of the frictional force here, and the frictional force is due to the viscosity of air. Okay, and you result what? You result in a smoke ring. Okay, because the air is rotating here. So in 3 dimensions, they become a ring, and that ring will propagate out to a large distance. And this is easily demonstrated by the so-called air soaker. Now this is the demonstration. You can put some smoke inside the bucket, and you press it on one side, the air will come out with a smoke ring, okay? And the smoke ring will propagate at a large distance in air. That is very interesting. Now, what actually happened is like this. Now, if the left-hand side, this is a schematic diagram only. The left-hand side is, you imagine the air is not having any viscosity. So when air comes out, it simply displaces the surrounding air without introducing the rotation. But with viscosity, when the air comes out in the right figure, it sets, because of the frictional force, it just sets the surrounding air into rotation, and that causes smoke ring. Okay. Now you also can see the so-called jet vortex for the airplane. Now because for an airplane with wings shaped like this, a small angle of tilt, there will be a high velocity of flow on the upper side and low velocity of flow on the other side. So the angular momentum of air, because there's a high velocity on the top, there will be essentially a clockwise flow of air. So the angular momentum of air will be in the so-called clockwise direction. But initially, when the air is far away from the airplane, there should be no such vortex, right? The vortex arise, the angular momentum arise when the air meet the airplane, meet the wings of the airplane. So by conservation of angular momentum, we cannot create air with the clockwise momentum. There should be a counterclockwise momentum to balance that. And it happens that there's a downwash of air that induce a shed vortex rotating in the opposite direction, so that the net vorticity in the flow domain is 0, or the total angular momentum is conserved. So if you see it clearly, when the airplane fly, if there's a mist, there's some fog or some cloud behind the airplane, you will see the shed vortex. The shed vortex is going to get the frog rotate and make it visually appearing. Okay. I would like you to see a simplified, because this phenomenon is quite interesting. So I may let you see a small section of Hoxiofei, which explain how this happened. I'm sorry that the video is in Cantonese, so some of you may not be able to understand, but I just shared it with you with fun, and that will not be tested in exam, so don't worry too much about it.
哇！你都幾勁喎打機，係啦，心講你要逼我啊！我要出波動拳，你有冇啊你？我深藏不露啊！
對住裙底，
喂，錯幾都錯唔到波出嚟嘅，咪係咯，咁大隻都出唔到波，搞錯啊！唉，唔玩啦！搞錯啊！咁渣嘅你，
唔係大隻咗，係你咗。
錯幾都錯唔到波出嚟。
出大唔識，出大冇呢招，
唔識咪學咯，蠢到死！
大叔喺邊位啊？
我係阿龍，
邊位阿龍啊？
教你戳波動拳嘅龍，你兩個跟我嚟啦！
師傅，教我哋波動拳。
呢幾個資質太差，我要用啲道具先得。
道具，你道具，道具。
咩嚟㗎？求其揾個爛膠土，家長用過嘅保鮮紙咁款嘅。
波動拳。
哇！好犀利喎，但係我乜都睇唔到喎，係咪大風咋？
睇唔到啊！
梗係唔係啦，俾啲煙落去，你就可以睇到好清楚㗎啦。
哦。
波動拳。
哇！睇到啦，咁
見到啦啩？
阿龍師傅，點解你個波動拳咁勁嘅㗎？
就因為咁樣嘅，其實咧個波動拳係一個桶嚟嘅啫嘛。嗱，不過咧佢後邊咧見唔見一個好大嘅膜啊？咁咧仲有條橡筋喎。當我拉去後邊嘅時候咧，其實條橡筋咧有一個好強嘅力，將塊膜彈翻轉頭。好啦，塊膜面積好大嘅喎，一彈翻轉頭嘅時候，係咪將個桶裏邊嘅空氣咧推出嚟啊？
哦，係啊，係啊。
但係咧塊膜太大啦，但係咧個出口咧就好細喎。你有一個大面積嘅地方，將啲空氣推出一個細面積嘅地方，嗰啲空氣咪會加速咯。有啲似咩咧？有啲似針筒啊！一撳咧，針筒組口嗰度咧好尖嘅喎，咁嗰啲水咪咇一聲咁出嚟咯。所以咧就會將啲空氣加速到好快，嘣一聲打到好遠咯。
好犀利啊，師傅！好想學啊！
嗱，為咗訓練你兩個咧，我已經準備咗2個頭盔，你哋戴咗佢之後咧就可以互射噶啦。你唔係咁戴㗎。
我今次點樣？
比試好簡單，我同 Regina 咧會喺頭盔上面擺隻杯，然後鬥快用空氣炮射跌對方個杯啊 ！Regina 接招啦
！Round one start。
你可唔可以？
慢鏡睇一次，係 Regina 個杯跌先㗎，哈哈哈哈！
我唔制啊，要報仇
Round two start。你可唔可以射準啲㗎？
冇力㗎！
哇！我想問下你練緊啲乜嘢咧？你個視線咧其實冇咁高㗎喎，我想問下。
佢有呢個瞄準㗎，我冇。你有啊？你有啊？賴地硬，你睇下。呢個比賽唔公平，我再嚟過。
你有咩 咩唔公平啊？呢啲俾你訓練下啦啫嘛。
但啱啱咧，我食都食唔中喎。
其實咧，你見到個出口好窄㗎嘛，咁所以咧嗰個炮咧，其實個風咧係好集中喺呢個位置嘅。咁你眼界唔好，咁咪驗下眼啦，咁咪射得唔準咯。
唔緊要，去睇下眼科醫生啦。哎，唔係喎，但係咧，佢哋呢啲咧，只係俾啲小學雞玩嘅啫嘛，最多唔係吹低嗰啲紙杯。喺
呢個時候，我怕我都要鬆我支大炮出嚟㗎。條腰帶鬆咗啫，其實喺嗰邊。
哇！
呢支巨型空氣炮睇落真係好架勢，係咪大啲威力就會勁啲？等我揾啲紙箱去試下先。
我知係大唔大先？大。嗱，咁要你幫下手喎，你咧就固定佢。嗱，我哋咧就負責打冧前面啲箱。
大隻。
哦。
3、2、1 ，Go！
哇！只係用一炮，7米以外嘅紙箱就應聲倒地，好勁啊！嗱，慢鏡睇睇，煙圈成個波動拳咁款，啲紙箱一掂到個煙圈就頂唔住，冧晒啦！
喂，不過阿龍咧，我想問下，點解咧個體積大啲，威力差咁遠嘅？
嗱，你就講咗個重點出嚟，個重點就係體積夠大。走咯。嗱，咁個體積夠大咗咩咧？裏邊空氣多咯喎。其實咧，對一樣嘢嘅衝擊力咧，用咩嚟量度咧？要用動量嚟量度嘅。咁動量第一樣嘢，個空氣個質量咧要夠大。第二咧，個速度要夠高。如果個質量又大、速度又高嘅時候咧，咁個衝擊力咧就夠強噶啦。咁其實咧，呢一支炮咧就勝在裏邊夠多空氣，而且一個膜咧個面積好大，一推出去嘅時候都好快嘅，咁嘣一聲咁啊冧咗咯。
你塊面嘅面積你吹出去啊，一吹出去就會冧噶啦 ，OK？Go！ 好嘅，唔得啦。
唔好玩住先啦，喂，有啲正嘢俾你哋。喂，我有啲形狀俾你揀喎，三角形啦，有正方形啦，喂，心女真係最中意噶啦，唉，
我都冇得揀嘅，呢啲咁嘅形狀有咩用啊？
嗱，咁可以俾你感受下咧，俾唔同形狀嘅煙圈射到咧，會有咩感覺咯？
哦，
你先啊，你先啊！
點解係我啊？
好，俾你感受下三角形煙圈嘅威力嚟咯。
3、2、1。咦？點解係圓形嘅？
我哋之後分別試咗心形、正方形同星形，發現所有射出嚟嘅煙圈最後都變做圓形㗎。
點解嘅？係咪個大炮知道咧圓形先包得住你啊？
你傻嘅咩？你哋試嘅時候都係咁啦。
但係點解我哋頭先用任何嘅形狀噴出嚟都係圓圈嘅？
嗱，不如我解釋下點解會有煙圈先啦。嗱，當啲空氣喺個窿嗰度衝出嚟嘅時候咧，其實速度好高嘅。咁而周圍啲空氣咧，其實速度咧就好慢嘅，差唔多唔喐嘅。咁於是咧，出邊啲空氣咧就會兜一個圈，走翻去後邊填補翻個空隙㗎咯喎。但係原來空氣咧有摩擦力嘅，當啲空氣走翻轉頭填補個煙圈嘅時候咧，其實就會產生一個旋轉啦，因為摩擦力嘅緣故咧，兩邊嘅空氣就會有旋轉㗎啦。而呢個煙圈咧有一個穩定性，佢可以喺空氣上邊咧向前一路移動，好一個好遠嘅時間嘅。嗱，頭先你見到正方形出嚟嘅時候，嗰個煙圈係點㗎？佢出嚟嘅時候好似有啲形狀似翻個正方形嘅，因為咧喺呢個咁嘅出口嗰度嘅時候咧，其實佢哋嗰個氣壓咧同埋個速度咧喺唔同嘅地方都係唔均勻嘅。咁所以啲空氣彈到出去嘅時候咧，啲唔均勻嘅氣壓咧就會產生個震動。咁呢個震動咧就會慢慢咁將個正方形咧變形啦。咁後來咧，當啲震動慢慢減退嘅時候，個正方形咧就慢慢變成一個圓形，最後一個圓形圈圈吹出去啦。
哦，哇！不過要咁大支嘢嚟學波動拳都幾麻煩。
唔緊要啦，你屋企夠大啊，擺喺你屋企學咯。
打男朋友，打男朋友。
大隻贏咗。
Okay. So this is the end of this chapter, and we are then ready for the next chapter now. And the next chapter is on oscillation. Now here is the PowerPoint that I've just uploaded to the backboard. And we just have a simple description on the so-called simple harmonic motion. Okay, we still have 15 minutes to go. Now we suppose a block of mass is tied to a spring, which is fixed at the other end. So the spring has a force constant K, and the block has a mass M. We assume that this is a top view. We imagine the block to be at rest on a horizontal table, so that the oscillation is there without the presence of gravity. The gravity is downwards, but that will not affect the horizontal motion of the mass. So we plot a graph of the displacement of the block about the equilibrium position. Now the equilibrium position is where the spring remains unstretched. So when the mass is here at this position, the extension of the spring is 0. And the spring will therefore exert no force on the mass at this position. Now let's stretch the spring so that the mass is initially at the position A, beyond the equilibrium position. So this is the amplitude of the oscillation. We initially stretch it to a distance to extension A, away from the equilibrium position, and we release it. And what would happen then? Let's guess with our intuition. Before doing the mathematics, let's guess with our intuition. When we release it, the spring will be pulling the block back, right? So it will pull the block back and will back to the equilibrium position. But somehow at the equilibrium position, the block acquires some speed because it's being accelerated by a spring for some distance, right? So even at the equilibrium position where the block is no longer exerted by the force of the spring, the block still has some speed. So it will overshoot the equilibrium position, and it was compress the spring. So when it compresses the spring will decelerate its motion, and until at this point, the block will be momentarily at rest. All of its velocity will gone, and the total energy, the total kinetic energy will be absorbed by the spring as potential energy. Okay, so that assume another turning point, and of course the spring will now push the block back. Okay, so it will push the block back, and will accelerate the block through the equilibrium position. And during this passage of the equilibrium position, the block still have some speed, and so it will overshoot the equilibrium position, and eventually it will decelerate and go back to its original position of release. So this will complete a cycle of oscillation. So initially it's being pulled back by passing the equilibrium position, and the spring gets compressed, and it goes to another stationary point, and the spring just pushes the block back through its equilibrium position and back to the original maximum displacement. So that will complete an oscillation like this. Now, if you draw this point by a smooth curve, if something goes like this, and we find that it is very similar to a cosine curve. And in fact, the solution to this problem is a cosine curve. Okay. Now, so we look for a particular solution like this. It has an amplitude A, and the change with time is a cosine factor. It goes as cosine omega naught t. Omega naught is the angular frequency, and the period t is the period of the oscillation. It's a time for the block to complete one oscillation. So because the argument, the combination omega t goes into the cosine function. So when t goes through one period, it goes from 0 to the capital T, which is one period. Omega t will just go through one cycle of the cosine function. But one cycle of the cosine function is 2 pi. So that means omega naught t will go from 0 to omega naught capital T, which is 2 pi. And so that means omega naught capital T is equal to 2 pi, and the period T is just 2 pi over omega naught. Now this we have learned before. It's just the same as the circular motion. If the circular motion has angular speed omega, then the corresponding period will be 2 pi over omega. And this is just the same relationship. Okay. Now, but this cases, this solution is just for the special special initial condition where the block is released from rest. We stretch the spring and we release the block from rest, and that would be the solution, right? But how about if I do not release the block from rest? If instead I give the block an initial velocity, I give it a kick so that it has an initial velocity. So how would it move? So how do we specify the initial condition, the initial velocity and the initial position in a more general way to obtain the solution? Now, this is the problem that we are going to deal with. We were going to find a general solution to this problem. Now, this is the oscillation of the spring that we studied, right? It attaches to a wall and is allowed to oscillate horizontally about the equilibrium position. Now, the restoring force, we assume it to be a Hookean spring so that it is proportional to the displacement. Now, the displacement is actually extension of the spring. The amount by which the spring is stretched or compressed. The length by which it is compressed or stretched is the extension x. Okay, and in this situation, because we count the displacement of the body to be from its equilibrium position, so the extension of the spring is equal to the displacement of the block. Okay, so the force is proportional to x, and the proportional constant is k. This is the force constant, and the minus sign is just says that the force due to the spring is in opposite direction to the displacement. So when the block moves to the forward direction, the spring is trying to pull it back. And when the block moves towards the spring is trying to push it back. So it's always in opposite direction to this displacement. So that's why there's a minus sign. And the equation of motion is specified by Newton's second law. The net force is just minus kx, and that is just equal to m, the second derivative of the displacement with respect to time. That is the acceleration. Now, for simplicity, we define the angular frequency to be square root k over m. We define omega naught to be square root k over m. Now, don't ask me why we define it like this. We eventually will find that the omega naught will correspond to the angular frequency. So let's define it with k over m square root. And with this definition, we move the m to the right-hand side, and k over m is omega naught square. So the differential equation becomes the second derivative of x with respect to time equal to x itself multiplied by a negative constant. The negative constant is minus omega naught square. Now, what kind of function will satisfy this equation? We want to ask. The equation is telling me to find a solution such that upon two differentiation of that solution, we returns you with the solution itself, but with a negative constant. So what kind of function will satisfy that requirement? Now, that reminds you with the supplementary mathematical notes. When we learn about supplementary mathematical notes, we learn about the cosine function and the sine function. When I start with the cosine function, I do a derivative of it. The cosine becomes minus sine. And because of a chain rule, there is a factor of omega naught coming out. And we differentiate it once more, the sine becomes a cosine again. And there's another factor of omega naught coming out. And together with this minus sign, it becomes minus omega naught squared cosine. And again, if we start with a sine, we differentiate it, we get a cosine with omega naught. And we differentiate again, we get minus sine and with another omega naught. So again, we get minus omega naught squared sine, right? Now you see, after the differentiation, the cosine go back to a cosine, the sine also go back to the sine, but with a negative constant of omega naught squared, minus omega naught squared. So that means both the cosine omega naught t and the sine omega naught t, they are the solution. And in general, we can say that the linear combination of these two solutions is also a solution to the problem. Now, why? What is called a linear combination? If x1 stands for the cosine and x2 stands for the sine, then if they multiply by an arbitrary constant c and d, and we sum them up together, this x is also a solution to the problem. Now, how can we prove it? Now, the proof is easy. We just substitute the x into the differential equation. On the left-hand side, we have the second derivative. So the second derivative acts directly on x1 and x2 because the differential operator is linear. So the constant doesn't matter, and the differential operator just operates in each term, in each of the terms in the bracket. Okay, so you operate on x1 and you operate on x2. But since x1 is a solution of the equation, the second derivative of it will give you minus omega naught square x1. And similarly, x2 is also a solution. The second derivative of it by the equation, it will give you minus omega naught square x2. And after extracting a factor of minus omega naught square O, we have C1 x1 and plus C D x2 inside the bracket. But that's exactly x. And if you compare the left-hand side and the right-hand side with the original equation, you'll find that x exactly satisfies the equation. So that we have the general solution now. The general solution is Cx1 plus Dx2. Now, this method is going to work because the equation is linear. What we mean by equation linear is that each of the term in the equation, it contains x or its derivative only once. There is no term that goes at x squared or dx dt squared or the second derivative square or square root or all those things. For each term, you either have x or the derivative of x, but that only appears once. You do not have a square, or you do not have a multiplying x or to x dx dt, etc. So that is called a linear equation. And the linear equation has such a property. If you find two solutions, which is a solution to the linear equation, then the linear combination of the two solutions will also be a solution to that equation. Okay, and in fact, in this case, the linear combination of this solution is the general solution for this equation. Now, what are C and D? They are the undetermined constant, and they are to be determined by the initial condition. Because now we have two initial conditions for the second order equation. We solve the second order equation. We start from the second derivative of x with respect to t. We integrate two times to get x. And that means there are two integrations. And for each integration, I introduce one integration constant. And so totally I have two integration constants. And these two integration constants exactly allow us to insert the initial condition. The initial condition consists of the initial position of the object, where the object is, and also the initial velocity of the object, with what velocity is the object moving initially. Okay, so but in the beginning of this lecture, we assume that C is equal to A and D is equal to 0. And that exactly corresponds to the solution with a 0 initial velocity. So we just release the object from rest. But the D here actually allows you to insert the information about the initial velocity of the particle. Now we can also write the solution in another form. Instead of writing it at a combination, the linear combination was cosine and a sine, we can also write the solution in terms of a cosine and then with a constant phase, which we call phi. Now let's see how we can do it. Now, instead of writing C cosine plus D sine, we write the solution as C cosine minus D sine. Now, the minus sign here is chosen only for convenience only. Okay, you can always make the D negative since it's a constant to be determined. You can always make the solution right by setting the D to be negative. Okay, so I prefer to write as minus D here. Now let's write this. Let's draw this triangle. We draw a triangle with the right angle triangle with the height D and the base equal to C. So D and C are the corresponding heights and the base of this right angle triangle. So we represent the coefficient C and D by these two sides. And the hypotenuse of the triangle will of course be equal to C squared plus D squared square root, which we denote it by A. A is defined as square root C squared plus D squared. Okay, and we define this angle here to be phi. And since from this triangle, the opposite side or the height of the triangle is a sine phi, while the base of the triangle is a cosine phi. So instead of writing as C and D, we can write the C at a cosine phi, which is square root of this thing, cosine phi. And we can write D as the square root of this thing, sine phi. Okay, the square root of this of C squared plus D squared is just A. Okay, so now having expressed C and D in terms of A and phi, we find such a combination. The combination is cosine omega naught t multiplied by cosine phi minus sine omega naught t multiplied by sine phi. But this is a standard combined angle formula. If we have cosine A cosine B minus sine A sine B, then it can be turned into cosine A plus B. Okay, and so now our A is omega naught t, our B is phi. So cosine omega naught t cosine phi minus cosine omega naught t sine phi become cosine omega naught t plus phi. This is the combined angle formula. And the square root here is denoted by A, as we say. Okay, so we now turn the solution into another form. This solution depends only on the cosine and also the amplitude A. The A is very apparently the amplitude, but there's also an initial phase. The initial phase goes with the argument of the it goes with the omega naught t. It is added to the omega naught t. Okay, so there's two forms of the same general solution. The first form is a combination of a cosine and sine, and the undetermined constant is C and D. Now, these are the constants to be determined by the initial condition. But there's also another way to write this solution. Instead of writing it in terms of C and D, we can express it in terms of the amplitude of the oscillation at the initial phase. They both represent the same solution. Okay, but whether this form is better or this form is better depends on the problem you are facing. In some of the problem, you may find easier to use this solution, while the other problem you may find easier to use the other form of the solution. Now, in the next lecture, I'm going to teach you how to choose CD or equivalent A and phi to satisfy the initial condition. So we have a full description of the motion of the problem. So let's stop here. If you have any